Good afternoon. Previous class we were discussing on digital communication channels, wherein we have seen the mathematical representation of any physical channel for analysis purpose, and what are the entropy functions associated with that we have seen in the previous class. So channel is represented in three different forms. One in the form of channel diagram, then a channel matrix P y given x, and JPM. So in three different ways we can represent a particular channel mathematically. And also we have seen the entropy functions associated with a channel: entropy of the source h of x, entropy of the receiver h of y, joint entropy h of x comma y, and two conditional entropies h of x given y and h of y given x. So in continuation with that, entropy of the source, entropy of the receiver, joint entropy, conditional entropies. Okay. So in continuation with entropy functions, let us continue to study the relation between various entropy functions. There are two important relations between these four entropy functions. One is the joint entropy. Joint entropy is related to entropy of the source and conditional entropy. H of xy is equal to h of x plus h of y given s. Equivalently, entropy of the receiver is related to the conditional entropy h of x given y. Okay. So mathematically, this is the relation between joint entropy with entropy of the source and conditional entropy. So joint entropy is sum of the entropy of the source and conditional entropy y given s, or it is also equal to entropy of the receiver plus entropy of the conditional entropy x given y. Okay. So mathematically we can prove this, and sometimes this proof is being asked in a few of the question papers, wherein it is simply mathematics. Okay. So by definition, of conditional entropy, right, h of y given x is, this is by definition, okay, joint probability, and this is the log of conditional probability. Base is default 2, and we have the relation between conditional entropy and the joint entropy by the probability relation. So with that, this 1 divided by p of yj given xi is given by, okay, from this 1 divided by this is reciprocal of this. So replacing 1 divided by p, this conditional probability, by this ratio, what we get is, okay, that is replaced by p of xi divided by p of xi comma yj, and then this is like log a by b, where a is given by 1 divided by this joint probability, and b is 1 divided by that p of xi. Okay, this is b. So this ratio log a by b can be split into log a minus log b. Okay, and this common is split into that a and b. So this is the relation for log a minus log b. Okay, and this summation of j equal to 1 to n p of xi yj is, okay, j is varying. J is varying means in a JPM, j is column. So column is varying. It means that we are performing addition of JPM elements row wise. So if you add, by the property of JPM, if you add the row of any particular row of a JPM, we get the probability of that input symbol. Okay, if you add any row of the JPM, okay, what we get is probability of the corresponding input symbol P of xi. Okay, so this relation, this j, okay, j varying 1 to n P of xi comma yj is replaced by P of xi, and summation I varying from 1 to m remains as it is. So if you look at this relation, this is a joint entropy h of xy, this is h of x. Okay. So first summation is h of xy, second is h of x. So therefore h of xy is h of x, okay, plus this. Okay, if it goes that side, it is plus this. On the same line, we can prove the output entropy and the conditional entropy. Simple mathematics. Second relation is this entropy of the source is always greater than or equal to the conditional entropy x given y, or entropy of the receiver is always greater than or equal to the conditional entropy y given x. Okay. So two relations with respect to entropy of the source and entropy of the relation. So how it is being proved mathematically is, we take this difference h of x minus h of x given y, and we are substituting the basic relations and then applying, okay, taking this common, we have made log a minus log b, this, and log a minus log b is log a by b relation here, okay, and this x given yj conditional entropy is replaced by, okay, x given y, that is probability of xi given yj is joint probability divided by probability of the conditioning event. Okay, so this x given yj is replaced by this, and this xi is kept as it is. Then we have studied logarithmic inequality. So converting this base, so base for all this is by default 2. Okay, log is base 2 here by default, and this base 2 is being replaced by base e, natural logarithm, which we have studied in logarithmic inequality. Okay. So replacing this log to the base 2 to base e, we get this log e to the base e is 1, and converting this base will come out to be denominator part of log 2 to the base e, and this log to the base 2 is now replaced by natural logarithm, and to that we are applying logarithmic inequality. So wherein natural logarithm of 1 over x is always greater than or equal to 1 minus x, and this is holding equality only when x equal to 1. So this is a logarithmic inequality which we have studied in unit 1. Okay, wherein, so to this natural logarithm, okay, with x being p of xi into p of I divided by p of xi, that is the x. So this natural logarithm is considered as 1 by x. This is natural logarithm of 1 by x, can always be written as greater than or equal to this term, and this is 1 minus x. Okay, 1 minus x by logarithmic inequality, and we are manipulating this. Okay, so this summation multiplied by 1 is the same, and the whole summation multiplied by this, wherein p of xy cancels, and what remains is p of xi into p of y. So this I varying from 1 to m, p of xi. Okay, I is varying here, in the sense it is column wise addition, and this is row wise addition. Okay, column wise addition and row wise addition. So if you look at this, this is sum of probability of all the elements. This is sum of probability of all the input symbols. This is sum of probability of all the output symbols. So sum of the probability of the input symbol is 1, sum of the probability of output symbol is 1, sum of the elements of all the elements of JPM is 1. So this is also 1. Okay, this is a multiplication also is 1. Okay, so 1 minus 1 turns out to be 0. So h of x minus h of x given y will be greater than or equal to 0, and that can be written as h of x will be greater than x given y. On the same line, we can prove this equivalently by the same mathematics. So, and this equality holds good when the input symbols and output symbols are statistically independent of each other. Simple mathematical proof. Now, what we studied so far was with respect to any physical channel. Okay, any physical channel. This is a channel, maybe wired or wireless, to which there are M symbols and there are N output symbols. Okay, this channel is mathematically represented by channel diagram or channel matrix or giant probability matrix, mathematical representation of a channel. And associated with every channel, we have entropy functions h of x, h of y, h of xy, giant probability, and conditional probability x given y and y given x for entropy functions. Okay, and also we have studied the relations between these. Okay, first relation is the joint entropy is h of x plus h of x given y. This is also h of y plus h of y given x, one relation. Second is entropy of the source is always greater than or equal to h of x given y, and entropy of the receiver is always greater than or equal to h of y given x. So these are the relations which we have studied as a part of entropy functions. The 2 points we have covered: mathematical representation of a channel, and second is entropy functions and their corresponding relations. On this, let us have one problem. Determine all the different entropies of a channel represented in the form of JPM and verify their relations. On this, okay, there is a problem. So what this problem is, a channel is described by JPM. We can represent the channel in 3 different ways, either diagrammatic or channel matrix or JPM. So this channel matrix is always a probability, conditional probability matrix. JPM is joint x comma y is a JPM. And this is diagrammatic representation. Okay. So given the channel represented in one of these 3 forms, we can do all this analysis. Okay, we can evaluate those parameters based on which we can draw certain conclusions. Now what is given in this problem is a particular channel is described by JPM, whose parameters are given here. Okay, and given the channel in the form of JPM, we'll have to find out all these entropy functions and verify these 2 relations between the entropies. Now, if you look at these elements, the size of this JPM, is there are 5 rows, 4 columns. So that means the input symbols are 5, x1, x2, x3, x4, x5. Output symbols are 4, y1, y2, y3, y4. So that means the input and output symbols are different. Okay, M and N are not same. So such a channel whose joint probability values corresponding to the input and output symbol are listed here. This is how the channel is described. So using this, let us find out all these parameters. In order to find out h of x, what we require is, we require a probability of all the input symbols, and by making use of the property of JPM, okay, we should find out all the probabilities of input symbols P of x1, P of x2, x3, x4 and x5. Okay. And how to find out probability of input symbols using JPM is row wise addition. So if we add all the elements row wise, what we get is probability of input symbol. Through that we can compute h of x. Similarly, h of y, we require probability of all the output symbols. So adding column wise, we get P of y1, P of y2, P of y3, P of y4, and accordingly we can find out h of y. Joint entropy, already elements are there. All these probabilities are there. So direct applying the entropy equation to this entire matrix. And then we should make use of the probability relation, find out these conditional probabilities and then apply the relation. So let's look at one by one. We know that adding elements of JPM row wise, what we get is input symbols. Okay. So row wise addition of these four elements. Okay. Row wise addition of these four elements. So row wise addition will give us probability of input symbols x1, x2, x3, x4, x5, 0.4, 0.13, 0.04. Okay. And then accordingly, this is what is probability of set of probabilities of input symbols x1, x2, x3, x4, x5 respectively, and accordingly we can compute h of x. Similarly, adding elements of JPM column wise, what we get is P of yc. Column wise addition, 4 columns, so 4 values. So with these two, we can calculate entropy of the source. Okay, P of xi log 1 divided P of xi comes out to be 2.022 bits per symbol. Similarly, entropy of the receiver. Okay. Now, joint entropy we can directly calculate. Joint entropy calculation is missed here, or is it calculated? No, joint entropy is missed. Okay, anyhow. So joint, how to calculate joint entropy is how to calculate joint entropy h of xy is we should make use of all these probabilities. So 0.2 log 1 by 0.2, 0.2 log 1 by 0.2, 0.1 log 1 divided by 0.1, okay, 0.01. So how many 0.2s are there? 1, 2, 3. So 3 times 0.2 log 1 divided by 0.2. How many times 0.1 are there? Only once. 1, 2, 3, 4. 4.01. So 4 times 0.01 divided by log of 1 divided by 0.01. So likewise, we should take up every element. We should see to that 5 into 4 total, all the 20 elements, use the probability values and find the entropy called h of xy. So that part calculation is not in this answer. We should calculate separately. Okay. Now, in order to find out these conditional entropies, we should make use of the relation P of x given y is P of xy divided by P of yj. So every element P of xy has to be divided by the corresponding probability of output symbol. Okay. So every element of JPM is divided by P of y1. This is divided by P of y2, divided by P of y3, 0.3, divided by P of y4. So what we get here is P of x given y. So using these values, we can calculate h of x given y. Okay, using the relation. So joint probability element and conditional probability element. So this first joint probability element log of 1 divided by this conditional probability element. So which we should apply to entire matrix, and this is what is h of x given y. Similarly, y given x. Okay, every row of a JPM is divided by P of x1, P of x2, P of x3, P of x4 and P of x1, and accordingly we get this matrix, and applying the relation to this, what we get is h of y given x. Okay, and if you see this, if you add this, what we get, actually we should calculate h of xy also separately, and these relations come out to be equal. And here if you look at h of x is 2 point something, h of x given y is 1.9 something. Okay, so it is greater. H of y is also greater. So all the relations we can prove. So given a channel represented in the form of JPM, we can calculate all the entropy values and verify the relations. For any channel matrix, we can verify all these entropy functions, calculate and verify the relations. So that's an example. So another point about the channel, okay, like entropy functions, we have one more parameter called mutual information of a channel. So these entropy functions will indicate some information related to any particular channel, wherein if you take h of x, entropy always indicates average information per symbol. Average information per symbol is what we call entropy. And entropy of x is the source. On an average, h of x indicates on an average how much amount of information every symbol, every input symbol is representing, is conveying. Okay, so that is given by h of x. Similarly, h of y is among the so many received symbol, on an average how much information we receive from each one of the symbols on an average. Okay, that is what we call entropy of the receiver. So if you look at this parameter, the entropy h of x represents average information needed to specify one input symbol before observing the channel output. So there is no output part in this, it is only input. So we are transmitting the information through this channel, okay, and we don't know, we are not at the output side, we are at the input side. So for a channel, we know input symbol probabilities, okay, and on an average, how much information is needed to specify every input symbol is given by h of x. So before observing the channel output, we don't know the channel output, we have not yet received the channel output. So h of x represents average information needed to specify one input symbol, each one of these input symbol before observing the channel output. And this is also h of x itself. This is only h of x which is not conditional, but this is a h of x with certain condition. So h of x given y is also related to entropy of the input symbol, but we know the output, we have received the output symbol. So the conditional entropy h of x given y represents on an average, okay, information needed to specify one input symbol after observing the channel output, because we have received the input, we know the output symbol received. So this is, we don't know anything about output, here it is, we know the output. So both these entropy functions are indicating average information needed to specify one input symbol. Here also average information needed to specify one input symbol. But this is before observing the channel output, this is after observing the channel output. So on an average, if you look at, okay, this h of x is before observing, h of x given y is after observing the output symbol. So on an average, observation of a single input provides these many bits of information. Okay, so observation of a single output at the output will provide h of x minus h of x given y bits of information, and this difference, with this difference we call it, what we call it as a mutual information of the channel, which is defined by the difference between these two entropies. Entropy, average information needed to specify a particular input symbol before observing the output and after observing the output. So that difference we call it as mutual information of channel. And this has got certain properties, this mutual information, this difference of h of x and h of x given y has got certain properties. So mutual information of a channel is symmetric, okay, which means that before average information needed to specify input symbol, okay. So we are at the input side. The same thing can be analyzed being at the output side. Average information needed to specify every output symbol, each one of the output symbol h of y can be thought of as, okay, before knowing this and after knowing this input symbol transmitted. So that is symmetric. I of xy is equal to I of yx, right, wherein I of xy is given by the relation difference in these two entropies, and we can prove this relation mathematically, wherein h of x is this definition, okay, conditional entropy is this definition, and this is the difference as usual, and we are taking common of this p of xi given yj, p of xi which is common, well, mathematics, okay. So I of x is taken common, and that log a minus log b is given as log a by b here, and applying this Bayes rule, okay, this p of x given yj using Bayes rule of probability, it is p of xi, okay, into p of yj given xi divided by p of yj. This is a Bayes rule wherein we can change this conditional probabilities, okay. The conditioning and conditioned events can be swapped using this Bayes rule. So with that, okay, so this equation, this ratio can be represented by this, and again split this into two using log a by b as log a minus log b, and that is what is h of y minus y given x, and that is mutual information yx. So it is symmetric. So mutual information of a channel is always symmetric. Both are the same. Either we can take I of x y or I of y x. Both are the same. Mutual information is always, second property is that mutual information is always non-negative. Okay, it can be either zero, no information associated with a particular input symbol, or some information associated with a symbol. It cannot be negative. Either it can be zero, worst case, which indicates no information, or there will be some information which is always positive. Okay. So this is again proved using the same logarithmic inequality, wherein we consider this basic definition, apply the basic definition, log a minus b is taken as a ratio, converting this base 2 to natural logarithm here, okay, with this ratio, and apply this logarithmic inequality, same concept, okay, which comes out to be 1 minus this. And if you look at this, okay, so wherein we arrive at only probability of input symbols, probability of output symbols, okay. So sum of input symbols, sum of output symbols, that's always equal. Sum of elements of all the elements of JPM, that is also 1. So 1 minus 1 becomes 0. So I of xy is always 0. Third property is mutual information of a channel may be expressed as, okay, may be expressed as entropy of the channel output. So since I of mutual information is symmetric, okay, we can always write, okay, the relation in terms of I of xy. Mutual information of a channel is related to joint entropy of the channel and channel input and channel output. Joint entropy related to channel input and channel output. So this mutual information is related to joint entropy and entropy of the input and output symbol as this relation h of x plus h of y minus the joint entropy. Okay. So where this joint entropy is the entropy obtained from JPM. So it's again a mathematical proof wherein we are applying the definition of h of x, h of y minus, we are applying this definition. Okay. We are writing initially h of xy. H of xy is 1 divided by pxy. And what we are doing here is we are multiplying and dividing by. This is as good as p of xi into p of y. P of xi into same ratio. So it's as good as multiplied by 1. Okay. Multiply and divide by the same for the definition of h of xy, which doesn't change the h of xy value. And to this mathematics is applied. So this and this. This thing is like a into b, okay, log ab. Log ab is log a plus log b. So that concept is applied. So one ratio is this p of xy divided by p of x comma y. Other ratio is this. Okay. So a is this, b is this. So log a plus log b. And with that, first summation comes out to be I of xy. Second summation is h of x. This third summation comes out to be h of y. And accordingly, we can represent this. And the same can be represented as a Venn diagram, wherein, right, this one circle is h of x, other circle is h of y, and this is what is mutual information. Okay, and put together is a joint entropy. Okay. So mutual information is related to entropy of the source, entropy of the receiver, and joint entropy. And only this part is conditional entropy. Only this part, output conditional entropy. So there are four properties associated with mutual information. Mutual information is symmetric, mutual information is non-negative, and mutual information is related to output symbol entropy of the channel output by this relation, and mutual information related to entropy of the channel input output, and joint entropy. Four properties. So this is what we have seen was three parameters: mathematical representation, entropy functions and their relations, and mutual information, I of xy. The next parameter associated with any physical channel is rate of information transmission over any discrete channel. What is the rate with which the information is transferred over a channel? Now, we have seen for any discrete channel what h of x indicates. So h of x indicates, okay, this h of x, what we obtain indicates average amount of information per symbol going into the channel. Okay, when we calculate h of x of these input symbols, on an average, how much information is going into the channel, that is available with h of x. Average information, okay, per symbol going into the channel is given by h of x, and this h of x, if multiplied by rate, okay, per symbol, that is what we call symbol rate, RS. Okay. If these symbols are sent at a particular rate, which is called RS, symbol rate, so multiplying this average information per symbol by the rate will give the rate of information inputted to the channel, which is bits per second. And this is what is the rate at which the data is inputted, data is inputted to the channel. And this channel has got its own behavior, and because of its behavior, there can be possibility of errors. So generally due to errors, it is not possible to reconstruct the input symbol sequence with 100% certainty. Okay, we can say that we can reconstruct this output we reconstruct the information at the output if the channel is ideal. Okay, so we can say that we can certainly reconstruct the original information at the output if there are no errors in the channel. But due to errors, we cannot 100% say, we cannot say 100%, we cannot certainly say that, okay, the output can be recovered at the output because of errors. So there is certain amount of uncertainty in reconstructing the information at the output because of errors. Now, how is that uncertainty represented mathematically? Okay, so uncertainty is expressed in terms of h of x given y. Okay, given y. Okay, so what this indicates is, because of this error, okay, we cannot 100% say, there is no certainty of reconstructing the original information at the output, and that is because of errors. So due to these errors, we can say that some information is lost in the channel. Okay, some information is lost in the channel. So this information lost in the channel, okay, information lost in the channel can be represented or can be interpreted as h of x given y. This h of x given y can be used as a measure of how uncertain we are at the input given the output, okay, which will indicate the uncertainty, how much uncertainty is involved in reconstructing the information at the output can be represented by h of x given y. So for an ideal errorless channel, there is no uncertainty. Okay, if the channel is ideal, then there is no uncertainty. So it means that no information is lost. Okay, so in that case, we can say that this uncertainty is 0. No information is lost in the channel. So this no information lost in the channel can be thought of as, okay, a parameter, okay, which will indicate that information lost in the channel can be represented with h of x given y. So we can define the amount of information transmitted over a channel, okay, is what is inputted minus what is lost. Okay, what is inputted minus what is lost is available at the output. So we can define the amount of information transmitted over a channel by subtracting the information lost in the channel. Okay, whatever is lost from what is fed, okay, is the amount of information going into the channel. So average rate of information transmission, okay, average rate of information transmission over the channel is, okay, this is what is inputted and this is what is the uncertainty associated with, okay, receiving the information. So subtracting this uncertainty due to errors from what is fed is, okay, the rate of information multiplied by symbol rate is what we call rate of information transmission. And this h of x minus h of x given y is simply the mutual information. Okay, that difference is the mutual information. So data transmitted over a channel, rate of information transmission over a channel is mutual information multiplied by symbol rate. And since this mutual information is symmetric, we can also write I of yx, okay, multiplied by symbol rate given by this. So mutual information will help in estimating the amount of information transmitted over a channel. The next parameter with respect to information transfer is how much is the capacity of a discrete memoryless channel, which you call it as channel capacity. So capacity of a noisy channel is defined as maximum possible rate of information transmission over a channel. So I studied the information transfer dt, which is mutual information multiplied by symbol rate, and when it is maximum, when this data transfer is maximum, that is what is the capacity. Okay. and capacity always indicates the limit. Okay, and here we expect that we should be able to transfer more and more information over the channel. So we expect this channel capacity to be the highest. So when can this DT, data transmission, can reach highest? That is the capacity. So information transfer can be lower than that, but what is the highest limit? That indicates the capacity. So it is a maximum possible rate of information transmission over the channel. And when can this be maximum? Maximum rate is possible when the source is matched to the channel. Okay, whatever is feeding this source is matched to the channel. And this with respect to network analysis, we can think of maximum power transfer theorem. Okay, when the source and the load match, the channel acts as a load and what is feeding to the channel acts as a source. When these two match, there is a maximum power transfer. So here it is, when the channel and the source which is feeding this channel, if they are matched, then data transmission becomes maximum. Okay? And that is the definition of channel capacity, which can be expressed in terms of mutual information. So two more parameters, redundancy and efficiency of channels, given by the relations. So redundancy is given by absolute redundancy divided by maximum, which is again h of x. Absolute redundancy is given by h of x except for arguments, divided by maximum entropy at the input side is h of x. So with mathematics it is 1 minus this ratio. Okay, and that ratio is simply this by mathematics. This ratio can be represented with data transmission and channel capacity. So absolute redundancy is 1 minus the ratio, data transmission divided by capacity is the redundancy, and 1 minus redundancy is the efficiency, actual rate of mutual information and maximum possible rate. So this is actual and this is maximum. Okay, so this ratio, actual by maximum, we call it as a efficiency. Then Shannon has defined his second theorem related to channels. His first theorem was related to source encoding, Shannon's binary encoding algorithm. Okay, so first theorem is noiseless coding theorem. Okay, related to source encoding. Second theorem is related to channel capacity. So we have already calculated this data rate of information transmission and maximum rate of information transmission, which we call it as channel capacity. So accordingly, when can we achieve this? Okay, and what are the parameters associated with this are represented in the form of theorem, Shannon's theorem on channel capacity. So given a source generating information at the rate r, the source is generating the information at a particular rate r, and a channel having this capacity, okay, maximum capacity c. If the rate of information transmission dt is less than or equal to the maximum capacity, then there exists a coding technique that enables transmission over the channel with as small probability of error as possible, even in the presence of noise in the channel. So if the information that we are feeding to the channel, okay, rate of information transmission, if it is less than or equal to the maximum capacity, then the probability of error is less, even if there is a noise. In case rate of information transmission exceeds the capacity, that is a negative statement. So this is positive statement, because when this is possible, when this is enabled, rate of data transmission less than its maximum capacity, then the probability of error is minimum. Okay, that enables transmission over a channel with very small probability of error. Okay, even if there is a noise. Negative part is, if this rate of data transmission exceeds the capacity, then the probability of error of receiving information becomes close to unity, probability of error reaches to unity. Okay, probability of error reaches to unity. So that means that we lose the information at the receiver when the rate of information transmission exceeds the capacity. So that is quite common that okay, whenever for any say fluid pipe, right? If the pressure, if you make the fluid to flow with a capacity which is more than whatever is possible to carry, then definitely there is always a probability of damaging the pipe and leakage and so on and so forth. Likewise, in this channel, okay, if the capacity is C and if you feed more, then the probability of error reaches to unity. So if DET is greater than capacity, rate of information transmission is greater than the capacity, then errors cannot be controlled by any coding technique. Okay, whatever may be the channel encoding techniques that we make use of, it is not possible to control the errors if the rate of transmission exceeds the capacity, maximum capacity. So that is what is negative statement, okay, given by Shannon. So with respect to any channel, we should estimate two parameters. One is what is the rate of information transmission and what is its maximum capacity, and we should try to keep this rate of information transmission slightly less than the capacity so as to recover the information correctly. If it exceeds this, then it is no coding technique, no channel encoding technique, no method of okay correcting the errors is possible to recover the information if the rate of data transmission exceeds the capacity. So error becomes close to, probability of error becomes close to 0. So these are the two statements, okay, given by Shannon for related to channel capacity, positive statement and negative statement. Now, how to estimate for a given channel represented in any of these forms, how to estimate this channel capacity, how to calculate the channel capacity of a particular channel represented with any one of these forms. Now for that, by definition, it is this: estimate the rate of information transmission using mutual information and then maximize that. Okay, when is this maximum? That is the fundamental definition, which is applied to any kind of channel represented in any one of these three forms. A special case of estimation of channel is given by another method called estimation of channel capacity using Muroga's method. Okay, so Muroga has given a easy method, okay, for estimation of channel capacity for a particular case. It's a general method of finding channel capacity with equal number of inputs and outputs. Under this special case, Muroga has given a simple method of estimation of channel capacity. General method is calculate mutual information, okay, and maximize that. Okay, maximize that. When can it be maximum? So that is the general method. But for this particular case, when the input and output symbols are equal, then Muroga has given a simple method. So how is that? Okay. So this is a channel matrix, P of y given x, or this matrix can be in the form of a diagram also. Okay. So all these are transition probabilities. So given the channel in the form of either channel diagram or channel matrix, what we need to calculate is some parameters, some quantities q1, q2, q3 up to qm, okay, are found out using the following matrix relation, simple matrix multiplication. So this channel matrix multiplied by the parameters to be found is given by, okay, the relation P11 log P11. P12 log 1 P12 P1m log 1 P1m. So these parameters multiplied by log. Okay, so it is not log 1 divided by. So hence all these values come out to be negative. All these individual elements of right hand part of the equation, matrix equation, they will be negative. Okay, so this fundamental relation, channel matrix multiplied by q values, and all these values are constants which are generally negative. So how many q values are there? Those many values we get here. Then the channel capacity C. Okay, through this we can estimate q values. I think it is small correction here. Here it is plus P11 log P11 plus P12 log P12 plus. So addition of all these values. So we get a column vector here. These are not, it's not a separate element. All this is plus. Plus is missing there. All these are plus. So what we get are those m values here, which is the evaluation of one particular row. This is plus here. All these are plus here. So with that we get a channel matrix, these values and this. So multiply this. This multiply one equation we get. Second multiplication, second equation. Likewise we get m equations. So m equations, these m values. Okay. So solving those m equations, we get m values q1, q2, q3 up to qm. Okay. And channel capacity is simply given by log to the base 2 of 2 power those q values will give the channel capacity. When multiplied with the symbol rate, we express the channel capacity in bits per second. So this is a Muroga's method, and using this method, okay, it's a simple matrix multiplication. Simple matrix multiplication, and solving those m equations, we get all q values, and substituting those q values in this simple equation, okay, we'll get the channel capacity. No need of mutual information, nothing here. No need to calculate any entropy value. Okay. So, but this is the case when m and n are equal. So, when an m and n are not equal, okay, we can go for the regular method of calculation of mutual information and find the maximum value of that. Okay, that is the general approach, finding the channel capacity. So, we will have a lot of problems on finding all these entropy values, mutual information, channel capacity. We find problems on all these in almost every question paper. Almost every question paper will have problems on calculation of entropy values, calculation of mutual information, calculation of channel capacity. Okay, in which a particular channel is given either in the form of a diagram or a matrix or JPL. Finding all these values, we get variety of problems in examination. So what is most important thing to understand is all these concepts which we have learned in the previous class and in this class are to be applied for a given channel represented in any one of these, okay, and find out all these parameters till the channel capacity is an important part of study of channels, that is estimation of channel capacity. Okay. So those examples we will take up in the next class. Thank you.